I need to click on the ADTT solvers. So as you can see, these are all the solvers. I think I already explained about each and every solvers earlier. Now once you click on the ADTT objects, uh, you will get a blank GUI. Okay. Now from here, actually, you need to start designing your own structure. Okay. So let's design a one simple filter using uh, using photonic crystals. Okay. So first what I'll do is I'll simply create a simple substrate. Okay. So I'll simply create a rectangle. Okay. I'll quickly do it because we are running out of time, so we need to we need to finish it off very quickly. So we need to first choose the rectangle. We need to define the rectangle property. For example, I have already taken as a rectangle, and I need to define the parameter of it. Okay. So let's say, for example, 15. So xyz is my coordinate. uh, x span is my 15 microns. Okay. Y span is, let's say, 13 micron, and z span, keep it same. Okay. So if I click on this, okay, you will end up this type of structure. Okay. So let me tell you, in numerical, this is my xy plane. This is my, sorry, this is my x-axis, this is my y-axis. Yeah, so better, for better understanding, okay, yeah, I'm just changing the viewport. So let's say, for example, if I go to the CAD diagnostic view, as you can see that this is my x-axis, this is my just a moment. Yeah, this is my y-axis. So this is my y-axis, and this is my z-axis. Okay. So this features is available in numerical right now, so you can very easily understand about the axis part. Okay, the layout part basically. Okay. Now coming back to this again, the 3D classic view. So this the rectangular part I have created. Okay. Now I will create some uh, first I need to assign the material first. Okay. That is very crucial. Okay. So for that case, what I'll do is I'll go to the material options. Okay. I will keep this material object as air. Okay. Simply just think that I'm assuming this rectangular geometry. uh, it has a property of air. Okay. That's why I put the index value 1. Then I'll create photonic crystals uh, inside this particular rectangular substance. So I'll simply click on this the structure again. I'll simply bring this circular options. Okay. Now what I'll do is I'll just first I'll check with the circle positions. Just a moment. Let me just find it out. Okay. So I'll go to the circle. Uh, I will see everything remains same. I'll keep x and y as 0. Let also 0. Now I'll change the radius of the circle. Okay. Now let's put it as a 116 uh, micron. So basically it's a 111.6 nanometer. Okay. You see, this is my circle, and it is completely embedded inside the rectangle. Now I'll place it because I want to cover the overall structure with my this particular circle. Okay. So what I'll do is I'll simply drag it and drop it at the corner. Okay. Okay. Can I see it? Yeah. So I can see this is okay. Uh, Now what I'll do is I will create an array of this circle to cover the overall, to spread it across the rectangle. So for that, actually, what I need to do is I need to give uh, the array. I mean, need to give the periodicity. Okay, how to do that? We have an option called the array. 56. So let's say 565 nanometer, or let's say 0.565 micron uh, is my periodicity or the lattice constant, and I'll change the column value or the row values. Maybe let's say 25 cross 22. Okay, and AZ lattice I don't need because AZ is across the Z direction. Okay, so I don't need to, because I'm not creating I'm creating a 2D lattice, so I'm not creating any three-dimensional thing. So that's why we are not simply bothered about the AZ part. Okay, and if I click on the OK, and now we can see this these things. Okay, how this pattern has been created. Okay, now that the trick comes. Okay, so what I'll do is I'll simply, because I know that I'm designing as a photonic I'm designing a photonic filter. Okay, so for that case actually I need to create some defects. Okay, I need to create some defects here, just by removing the some of the dots. Okay, so what I'll do is I'll just simply remove some dots. Okay, so let's take it from here. Okay, so I'll simply select all these dots. Sorry, very precisely I need to select the dots. Okay, just to showcase you how to create that. You can see that at the left, the object trees, the dots which you have, I mean the circles you have selected, is all are completely highlighted, and you simply click on the top of them and you just to simply click on the disable. Okay, now you can see that it's gone. Okay, now we have created a certain cavity. Okay, similarly, so this could be your input port. Okay, now I need a drop port. Okay, so how we can create the drop port? So we, again, the same method will follow. Okay, we'll just simply take it from here, let's say. Okay, yeah, so I'll just simply I just need to select these things. Okay, I hope you understood, I mean, how to do that. Anyway, I'm just deleting all these things. Okay, maybe I need to complete all other two also. These two also I need to complete. I need to disable it. Then only we'll be able to create a drop port here. Yeah, so I'll just simply disable it. Okay, now you can see that we are ready. We are already completed. We have created the drop port. Okay, now what will happen is still our job is not done. So if you look at the lattice, okay, so basically the actually lattice looks like so if you see like this, so this is my lattice actually. This is a simple, since it's a kind of a rectangular lattice. This is my first value. So this is my gamma point. This is my scattering point M, and this is the scattering point X. Okay, so I have, first of all, in the simulation actually I actually deleted uh, across the across the fx the fm directions. Okay, and also the gamma x direction. Okay, at the vertical also. Okay, this is my the lattice orientations. So go to the edit object. Now you have to select the material from here. Okay, so you need to select the silicon. Uh, okay, and need to click on the apply. Okay, then only able to see the see that all the materials have been applied, and you can see the rods. Okay. Yeah, so now what you need to do is you need to add some defect by changing uh, the radius. Okay, the radius of this region. Okay, if you change the diameter or change the radius, of course some defect will create it, and the light will simply get coupled from this waveguide to this waveguide, and it will start traveling without any diffraction. Okay, and that is the reason. Okay, I actually completed that design earlier, and so that I can showcase to you quickly the same designs I have created. Okay, so I hope you understand the part, this part, how to create the arrays, and how to omit and how to omit those rods just to create the passage. Okay, now you see that's here actually I have changed these three these three rods diameter, I have changed it. Okay, and that is the reason something will happen, and what will happen, you'll see it very quickly. Okay, uh, now just to give you the another thing, uh, that this is the source part. Okay, which I have used as a Gaussian sources. Okay, so this is my source part. You can see that I have defined the frequency. Okay, from 1.5 to 1.6. Okay, if you ask me how do I select it, because I know this will work for the 1.5 to 1.6. That's why. Okay, because I have taken it from a paper. So yeah, so similarly, you need a one monitor for that as well, just to detect the light. So I put a monitor here. Okay, so the purpose is to filter out or let's say to pass a certain wavelength. Okay, out of my input frequency band. Okay, once you run the simulations, what we'll see it, you'll see simply, you'll see if you look at the transmission monitor, you'll see that just change it. Yeah, you'll see that this wavelength, actually you see the transmission is 0.25. It's very low, but because it's a random structure, arbitrary structure, uh, it's not it's not at all optimized. But for that case, you see that only this peaks. Okay, because I've taken from 1.5 to 1.6, and you see this peak has the highest transmission. Okay, there's also some transmission is happening because I told you that it's not perfectly optimized. So uh, you can also create, you know, sharp optical signal. Okay, by designing this kind of structure. So that's how it's acting as a filter, because it's only passing this much of information. Okay, so this is how we can design this filter. And one small changes I have done. Okay, that is also arbitrarily, let me share it with you. Another way, actually, we actually change this peak, you know, peak wavelength. Okay, so by simply creating ring resonators. Okay, so let me just go back to the few options. Yeah, so you can see that apart from this waveguide, we create a micro ring resonator structure here. Okay, so if you do that by simply omitting the, you know, the rods. Okay, and then what you can do is simply, if you run the monitors, if you change, if you run the monitors, so you can see that how now how broader it became. Yeah, see, the pulse shape changes. Okay, so now it becomes broader compared to the previous one. Okay, so this is how you can change your you can change the filtering property of your structure. Okay, so and one interesting thing I want to showcase you, that's the animation, that's how, you know, the electromagnetic energy is propagating through the structure. So uh, so just a moment, probably I deleted this. Yeah. Mm, my deleted that. Probably I deleted that. Maybe I can simulate it once more. Uh, you need to right click on it, go to the edit object. Okay, go to the frequency and wavelength. Here actually you need to set the wavelength. Wavelength start to wavelength stop, you need to define. Okay, yeah. So I think this is the my output. Let me just run it. Is it running? I'm not sure. Yeah, here it's running. Yeah. So this is my input. This is my input frequency. Okay. Now see how the light is confining here. Uh, Inside this resonating structure, and very few light is passing through this waveguide. Okay, so anyway, because it's not completely optimized, that's why I'm getting very 0.25, I'm 25% transmittancy at the output port. Okay, but this is how actually it works. So you see that how the light is confined, still confined, but slowly it gradually it is dissipating. Okay, And that is the purpose, and that I'm see it the cavity, because of this cavity nature actually your pulse get broadened. Okay, because the Q factor of this cavity, okay, maybe this the cavity is not enough small, to hold a single pulse, okay, a single frequency pulse. That's why it's making the pulse broader. Okay, because completely randomly I just selected, I picked it up, and I just omit this those rods. Okay, and that's how I created the cavity. Okay, so that this is the way we can design the photonic crystal cavity as well. It's a good learning for us that uh, it's not so simple, of course. You need to understand like which rod I need to replace, or which rod I need to omit, by doing the calculations. I think one question I have seen in the chat box, at how to calculate the photonic band gap in for the photonic crystals. That's a complicated thing. Yes, that is also very much required to understand about the photonic crystal structure. The band gap actually we do using the dipole sources, not using the planar sources, or not using the Gaussian sources, because the the algorithm, I mean the uh, I would say the approach is a bit different, okay, compared to this simulation. This simulation will only come when you are sure that, okay, so this is my band gap, this is my this should be my operating wavelength. This only I need to inject, and then only you can do the rest of the part. Okay, so to understand about the wavelength, you need to run the band gap simulation at first. Okay, because I have taken it from a paper. That's why I didn't, because all the data was mentioned over there. So that's why I didn't find any reason to run the uh, photonic bandgap simulation. Okay, but if you're doing it by your own from scratch, then of course in that case you need to run the photonic bandgap simulation. Okay, yeah. So that's all for today. That's what I wanted to showcase, the capability and the tool demonstrations. I hope everybody find it very much useful.